Okay, guys at home, can you hear me and see the board okay? All right, I've already filled the first page of your notes in. We're starting chapter 4. Chapter 4 is all about polynomial functions and rational functions. I know you've done polynomials because it's a very simple mathematical expression that I know you've worked for a very long time. Did you guys in Algebra 2, before quarantine hit, get to do your roller coaster PBA? Did you get to do that? So this is basically polynomial. So I filled the first one in just because I know you know all of this about a polynomial, okay? All right, so guys, a polynomial is just a very nice mathematical expression where you have variables and constants that are attached by multiplication, and then you're adding all of these terms together. The word polynomial literally comes from the Greek word where poly means many and nomials mean term. It's literally just the sum of many terms. It is said to be one of the easiest mathematical expressions that we work with in math because the operations that are defined by a polynomial are very simple operations. If you look over to the side of your notes here, I don't have it written, but on your notes that I did, polynomials don't have horrible operations involved. They don't have division by a variable. They don't have negative exponents. They don't have fractional exponents. They don't have variables under a radical, which means there's no restrictions. There's nothing bad that could happen when you're working with a polynomial, okay? All right, when you first start working with polynomials, you probably classified them by the number of terms. Like a one-term polynomial was a monomial. A two-term polynomial was a binomial. A three-term polynomial was a trinomial. But as we get into higher level math, we tend to classify polynomials by their degree. And the degree of a polynomial is just the highest exponent or power on a variable. All right, the standard form of a polynomial is when the parentheses have been removed from the expression and it's all multiplied out and you have it in descending order. So you're going from the x squared term to the x to the just number, the x to the third to the x squared to the x to the just number. That is descending order. That is standard form of a polynomial, okay? The graph of a polynomial function. Guys, this is when, I don't know if you're a teacher, it's like you're dancing. It's the one up, one down, both up, both down, all that good fun stuff. Those are all the graphs of a polynomial function, okay? The graph is a smooth, continuous curve, which means it does not have any holes. It does not have any points of discontinuity. It doesn't have any sharp turns or corners or cusps. When you get to calc, you'll learn about a cusp. It doesn't have any of that. It's a very nice, smooth, continuous curve. And the reason it doesn't have any holes or jumps or points of discontinuity is because there's no bad x values in its domain. You can plug any number into this function, and it's going to create this nice, smooth, continuous curve. There's no bad x values. All right? So then they give you the fancy definition, which, guys, basically they say a polynomial function in one variable is a function that can be written in this form. A sub n times x to the power of n plus a to the sub n minus 1 times x to the n minus 1. But guys, this is literally like your 3x to the fourth plus your 5x to the third minus your 3x to the second power. It's literally just a polynomial expression written in descending order, where the a sub n's and the a sub n minus 1s, those are all your constants that are the coefficients, the number in front of the variable. All right, n is greater than or equal to 0. It's got to be an integer. You have to have whole number powers in a polynomial expression. There's no fractional exponents or negatives, okay? You have x is the variable. If a sub n does not equal 0, then that is known as the leading coefficient, right? The leading coefficient is -6. The leading coefficient is +1. The leading coefficient is 5x squared, which is what I'm talking about over here. LC is your leading coefficient, and LT is your leading term. These are all things that I think you've been asked to identify in a polynomial. Just make sure that when you are dealing with a polynomial, you have it in descending order before you go to pick out the leading coefficient or the leading term, okay? All right, so like I said, we tend to classify polynomials at this point by their degree. Degree 1 polynomials are our linears. Degree 2s are our quadratics, and so on, okay? All right, let me move this up so we can start practicing a few problems. Michael, this is all written down, so, all right?
I'm trying to remember what I was going to ask.
Go ahead.
Oh, wait. When you had the notes up, when you had the equation,
Yep.
and you had, why did you have like the dot?
Because if you can do this forever, it could be a degree 6, and then it's going to go to the 5th power, the 4th power, the 3rd power, all the way down to the just number a sub 0. But if it's a seventh power, then you'll have, it's just continuous. It goes all the way down to that just constant number.
So it's like n is like whatever the
highest degree is, that highest power. Exactly.
And then each time that subtracts by 1.
It just goes down, right? Yep, your x to the 7th, your x to the 6th, your x to the 5th, your x to the 4th, and so on.
So that's just supposed to fill in for like whatever n is.
Wherever we start at.
Okay.
Yep. Okay. All right. So guys, a couple of good things. The domain of a polynomial function, because it's this beautiful mathematical expression, the domain is all real numbers. Sorry, I couldn't fit this on the board anymore. All right. There's no bad x's. There's no number you can't plug into this function. All right. The leading term is a sub n times x to the power of n. That highest degree power that we started, that's your leading term. The term a sub 0 is your constant term. So he's usually the one all the way at the end by himself without a variable. A polynomial in standard form, the terms are listed in descending order. I know I filled this in, but I couldn't fit it on the board prior to this. All right, perfect. So guys, just remember, if you are a polynomial, you have no negative exponents, you have no division by a variable, you have no fractional exponents, and you have no variables under a radical. So if you look at these expressions, they want you to pick out whether or not it's a polynomial expression, and if it is, they want you to write it in standard form, if it's not already, and they want you to identify the leading term and the constant term. So guys, look at this function. Is this a polynomial function in standard form? Absolutely, right? So we would say yes. The leading term, who's that leading term, that a sub n to the power times x to the power of n? It's 3x squared. Your leading term is 3x squared, and your constant term, your just number, is negative 10. Okay? Well, look at this one. Is that a polynomial function? No. This is killing us right here. X to the 2/3 power. No fractional exponents, because if you guys remember, x to the 2/3, you can't raise something to a fractional power. How do you times something by itself a fractional number of times? Powers became roots and powers. So really, that's the third root of x squared. And now you have a variable under a radical, and that's a no-go. So this is no, not a polynomial expression. And again, I don't mean to fly, but I know what I'm saying. You guys already know. So I'd rather spend more time on just the new vocab they're going to throw at you. Okay, so guys, look at this one. Is this a polynomial function? Absolutely not. It's got an x to the negative 3, which we know is really 1 over x to the 3rd, and now you have division by a variable. So that is no way a polynomial expression. Again, polynomials should be simple. They should look pretty. All right, look at this one. G of x equals negative 5. Is that a polynomial function? Actually, it is. It's a constant function. This function only spits out the number negative 5, but that's a polynomial. It's beautiful. So this is a yes. And then what did it ask us for? The leading term? The leading term is negative 5. That's the only term that lives in this polynomial function. What is the constant term? The constant term is negative 5. It's the only number that lives inside of this function. All right, and then the last one, this is not in standard form. This is not multiplied out with the parentheses removed in descending order. So let's distribute. And you get that expression. No like terms, we're good to go. So yeah, that's actually a beautiful mathematical expression with no bad operations. So that's a yes. The leading term is 6x to the 3rd. And then the constant term, well guys, who's the number that's by itself at the end? 0. Okay. So again, nice and easy, just recognizing polynomials from non-polynomials. These are just, the ones that are no's are just mathematical expressions. We can't call them a polynomial. Their graph would not be the smooth continuous curve. All right, so guys, this is just a new word for us. Our book likes to talk about power functions, but at the end of the day, a power function is literally a one-term polynomial. All right, so a power function of degree n is a monomial, and a monomial is a one-term polynomial function of the form a sub n times x to the power of n. So if you think of each individual term of a polynomial like this, right here, 6x to the third, that's a power function. The negative 3s, that's a power function. Each individual term of a polynomial is what we call a power function. A power function has no adding and subtracting. It's just a power and multiplication going on. All right, and we're going to reference the leading power function all the time. Because when we start graphing these polynomial functions, the leading power function, the leading term, is how we figure out what the graph is going to do. So they're going to talk about that leading power function all the time. But guys, it even says, notice that we could also define a polynomial as a sum of power functions. It's a sum of terms, right? Each term of a polynomial is its own power function. Okay, so they want us to look at some power functions really quickly. Now again, I'd like to think you already know this about the graphs of polynomials, but again, they're willing to review it with you, so let's review it. So what they're asking you here is to explore a few things. We're not going to use a graphing utility, we're just going to use the graphs that they gave us, all right? Because it just takes too much time. But they have given you the graphs of y equals x squared, that's a power function, right? X squared, it's technically the parent power function. It's the parent to all parabolas. All right, we have the graph of y equals x to the fourth. That's a power function, right? Just x to the fourth. It's a one-term polynomial. That's the parent of all degree 4 polynomial functions. And then we have y equals x to the sixth. And then over here, we have the power functions y equals x to the third, right? That's the parent, the simplest form of all cubic functions. Y equals x to the fifth and y equals x to the seventh. So the first thing I want to do is just label who's who. So guys, I hope you realize that as the power gets higher and higher, obviously the bigger numbers you're going to get more and more quickly. So the higher the power, the steeper or faster it's going to be. So the widest one is going to be the lowest power. The skinniest one is going to be the highest power because it's creating the biggest numbers the fastest. So this is the graph of y equals x squared. This is the graph of y equals x to the fourth. And this is the graph of y equals x to the sixth. And then the same thing over here. The higher the power, the quicker it's going to grow. So the wider ones are the ones that are growing slower. So this is the graph of x to the third. This is the graph of x to the fifth. And then that's the graph of x to the seventh. So basically, we're comparing even parent power functions to odd parent power functions. So guys, right away, let's notice some of the differences. There's two things they really want you to concentrate on. Number one, the end behavior. Hopefully you guys remember that word. That's a word we use all the time. The end behavior of the graph is what is each end of the graph doing? As x gets really, really big or as x gets really, really small, what's the y value doing? What's the end behavior of this graph? All right, so if you notice on an even power function, the end behavior is the same. Both ends end going in the exact same direction on your even power functions. But on an odd power function, look at the end behavior. As x gets really big, this end ended up. As x gets really small, this end ended down. So on odd parent power functions, the end behavior is different. It's opposite. All right, and then another thing they're going to want you to concentrate on is what's happening around this x-intercept. As the graph approaches 0 from the right and left side, what's the graph doing? Do you guys notice this flattening out effect that is happening as the power of the degree got higher? Like here's y equals x squared, pretty smooth. Y equals x to the fourth, the power got higher. It started to flatten out a little bit as it went through that x-intercept. And then the graph of y equals x to the sixth, it got even flatter as it went through that x-intercept. The same thing over here. As this graph approaches 0 from the right and the left side, right, as you're converging on x becoming 0, what's the graph doing? Do you see this flattening out effect that the graph has? That's going to be something that we really have to pay attention to, and they're going to give it a name that they're going to reference a lot. All right, but notice, the higher the power, the more flat the graph got. All right, so guys, here we go. Let's do the even one first. Do they share the same shape? Yeah. They basically all look like parabolas, but only the graph of a quadratic can be called a parabola. Go ahead,
We
Michael.
have someone at the door.
Oh, come on in. Oh, hi.
Hi.
Oh, thank you. It's like Christmas. Beautiful. Thank you. Okay. Thank you so much. Oh, I love it. Thank you.
You're welcome.
Okay. All right. Do they have the same shape? Yes. All right. On the even ones, do they share any points? Yeah. They all actually go through the point 1, 1, 0, 0, and negative 1, 1. All right. Are they symmetric to the y-axis, x-axis, or the origin? Well, we can see the even ones are definitely symmetric to the y-axis. Right? For every xy that lives on the graph, so is the opposite of xy. What is the domain of even-powered functions? Well, guys, what should be the domain of any polynomial? It's all real numbers. I can plug any number I want in, and it's okay. What is the range of even-powered functions? Well, again, this is all before they've been transformed. They haven't been shifted up, down, left, or right, or stretched. The parent functions, their range is only 0 to infinity on a parent power function. Okay, guys, here's the big question. What happens to the graph as n, the exponent, increases? So as n, the power increases. So from a degree 2 to a degree 4 to a degree 6 and so on. As x goes to positive infinity or as x goes to negative infinity, what is the graph doing? So guys, what they want you to take away, and we've kind of discussed it, on an even power function graph, as x gets really big or as x gets really small, what's the y-coordinate doing on both ends of the graph? Both ends of the graph are shooting off to infinity. That just means that they have the same end behavior. On an even powered function, we should end in the same direction, either both up or both down. So I'm going to say EV is the same. They have the same end behavior. All right, but now they want to know what happens as x goes to 0. So guys, I already mentioned this. As x gets closer and closer to becoming 0 from the right side, and as x gets closer and closer to becoming 0 from the left side, you do this in calculus a lot. You approach an x value from both sides to see what the graph is doing. And what they want you to realize is as x gets closer and closer and closer to becoming 0, there is this major flattening of the graph the higher and higher the power gets. So as x goes to 0, there is a flattening out effect on the graph. Now let me tell you why, and this is going to be a new vocab for us. When you set an equation like y equals x equal to 0 and solve, how many times does x end up equaling 0? One time, right? You set it equal to 0, x is 0. But if you set a function like y equals x squared equal to 0, well, how many times does x actually end up equaling 0? Technically, x squared is x times x. So by the zero product property, I would set each factor equal to 0. So now technically, how many times does x equal 0 when y equals x squared is set equal to 0? 2 times. That is called a multiplicity in pre-calc, and the higher the multiplicity is at an x-intercept, there is going to be this flattening out effect. So on the graph of y equals x squared, like, yeah, it starts to get a little flat and then it goes through. But then when you set x to the 4th equal to 0, how many times are you really getting x equals 0 as an answer? Well, technically, x to the 4th is x times itself 4 times. So I would set this equal to 0, I would set this equal to 0, and I would set this equal to 0. So technically, you get x equals 0 as a solution 4 times. So the higher the multiplicity is at that x-intercept, the more flattening out effect there is on the graph. And we're going to be talking about multiplicities all the time. All right, so you have to realize that the higher the multiplicity is at that x-intercept, the more flat it's going to get. And there's going to be one other thing we talk about the multiplicity at. If you notice, when the multiplicity is even, right, like x equals 0 2 times, x equals 0 4 times, X will equal 0 6 times. Guys, as it goes through that x-intercept, it flattens out, but on an even graph, it doesn't cross over the x-axis. It doesn't come out the other side. It literally bounces back in the same direction from which it came. So an x-intercept at an even multiplicity, we call it a bounce. It doesn't actually cross over the x-axis at an x-intercept with even multiplicity. And we're going to talk more about that later. All right, guys, let's do the odd graph. I'm not going to write it down just because I have to move my graph, but it's the same questions. So if you look at the odd ones, do they share the same shape? Yeah. They all share the same one up, one down, flowing, nice, smooth, continuous curve. So that would be a yes for the odd ones. Do they share any points? Yeah, they do. They all pass through 0, 0, 1, 1, and negative 1, negative 1. So 1, 1, 0, 0, and negative 1, negative 1. All of the odd parent functions pass through those points. All right, on the odd ones, are they symmetric to the y-axis, x-axis, or the origin? Well, guys, the odd ones have symmetry to the origin, actually. For every xy on their graph, the opposite of x, the opposite of y lives on their graph. All right, what is the domain of odd power functions? Same thing. What's their domain? All real numbers. That's the beautiful thing about a polynomial is you can plug any number you want in and nothing bad should happen. All right, and then, where am I? What is the range? Well, guys, this one, look who comes out of an odd-powered function. He's going to infinity. He's going to negative infinity. So all real numbers. All real numbers is now your range, right? The even ones only had 0 to infinity coming out. Go ahead, Michael.
And is that the same for the domain?
Domain is all real numbers, yep.
So they're both
all real numbers, because polynomials should be all real numbers. All right, and then the big question is, what happens to the graph of n on the odd ones as the power increases, right, as it goes from an x to the third to the x to the fifth to the x to the seventh, and x goes to infinity or negative infinity. So basically, guys, what's the end behavior of an odd function now? So let me do this. On an odd one, end behavior is this end is going to infinity, this end is going to negative infinity. So the end behavior is different, or say the opposite. And again, hopefully you know that. All right, but now again, what's happening as x goes to 0? As x approaches 0 from the right side, and as x approaches 0 from the left side, there's that flattening out effect again. And again, the higher the multiplicity, right? X is going to equal 0 3 times. X is going to equal 0 5 times. X is going to equal 0 7 times. The higher the multiplicity, the more of this flattening out effect that is created on the graph. Also, if you notice, when the multiplicity at this x-intercept was odd, not only did it flatten out, but it still crossed the x-axis. It started up here, it flattened out, and it crossed and ended down here. That didn't happen on an even power function. It never crossed. It started up here, it flattened out, and it ended up here. So the multiplicity, again, when it's odd, you will cross over at that x-intercept. When the multiplicity is even, you will just bounce. You will not cross over the x-axis at that x-intercept, and that's huge for us, okay? All right. How much time we got? 5 minutes? All right, so let me just give you a summary. So just to give you a quick summary, your even power functions, they had symmetry to the y-axis. Their end behavior was the same, either both up or both down. And the even ones contained the points, what was it, negative 1, 1, 0, 0, and 1, 1.
Yeah.
Okay? Odd power functions, they had symmetry to the origin. All right, their end behavior was the opposite. One end was up and one end was down. And then all of their functions, no matter what power they were, again, these were parents before they were transformed, all of them contained the points negative 1, 0, 0, and 1, 1. Okay, I'm gonna try and sneak this in. Our book is huge on graphing functions using transformations. I don't really love transformations, but they want you to be able to recognize them. So they want you to be able to graph these parent power functions once they've been transformed using actual transformations. So guys, look here, we had to graph this one. Who was his parent? Was his parent the graph of y equals x to the fourth, or is his parent the graph of y equals x to the fifth? X to the fourth. Which means it's even, so we know his end behavior is the same, and we know his parent passed through the points negative 1, 1, 0, 0, and 1, 1. We know that his parent passed through these. So guys, now all we're going to do, I have 2 more minutes. I'm taking it. We know that his parent was transformed, so recognize the transformations. This negative 2 on the outside of the function, who did he transform? The x coordinates or the y coordinates? The y's. So that would be negative 2 times the y's, causing an x-axis reflection and a vertical stretch by a factor of 2. This plus 1, on the inside of the function, who did he affect? He affected the x's. But we know whatever happens to x is the opposite. So he didn't really add 1, he minused 1. So now guys, all you have to do to get your transformed graph is take the 3 original points and make these changes to their x and y coordinates. So take his x coordinate and minus 1 from it. That's now negative 2. That's where he's been transformed to. Take his y coordinate and times it by negative 2. That's this point's new home on the transformed function's graph. All right, take 0, minus 1 from it, negative 1. Take 0, times it by negative 2, and you get 0. This point has now been moved here on this new function's graph. And then the last one, take 1, subtract 1 from it, that's 0. Take 1, times it by negative 2, and you get negative 2. When you plot these points on the graph down here, you have your new transformed graph. And again, it's going to look like an upside down parabola, but it's a degree 4. They don't really form parabolas. It's just going to look like it. And there's going to be a flattening out effect there. I apologize for rushing that, but there are homework questions on this, so I wanted to make sure I get to it, okay? All right.